Welcome to Lecture 13, Improper Integrals. So as an overview, let me ask you a question. How do we evaluate the following integrals? So this first one is interesting because we know how to integrate e to the negative x, but how would we integrate it from 0 to infinity? Now, we've never seen integrals where there's an infinity in one of the limits. So this function is going to look something like that. And now we want to take the area, it's going to end up being a finite amount of area under this curve, but it goes on forever. Okay, and the second one, so that this is e to the negative x. And the second one looks innocent, but when you sketch it, you realize that this has a vertical asymptote at 0. So this is 1 over x squared. So what we're doing is we have this, I guess between 0 and 1, it's going to eventually stop on the right-hand side, but the left-hand side we have this vertical asymptote this way. So here we have a horizontal asymptote, and here we have a vertical asymptote. And I picked these functions that both of these integrals are going to exist, meaning these regions do have finite area. Now I could find ones that don't have finite area. If this, instead of e to the negative x, if this had been 1, then not surprisingly that area underneath the curve 1 is going to be infinite. And even if I had picked 1 over x instead of 1 over x squared, it's not obvious, but this integral is not going to exist. Okay, so type 1. So there's two types. One of them corresponds to a horizontal asymptote, or an infinite domain of integration. The other one's going to correspond to a vertical asymptote. The first one, let me give two definitions. If the infinity is in the upper limit, then we define this integral to it's just the limit. We fix a, and it's the limit of the integral from a to b as b goes to infinity. Secondly, if the infinity, or I should say the negative infinity, is in the lower limit, then the integral is defined just to be the integral from a to b, and now the lower limit is going to negative infinity, so it's this limit. Okay, so let me sketch pictures of this. I don't think this should be too surprising, but so the first one says we are going to fix a, and then b is going to be our thing that's going to go off to infinity, and we are measuring the area under the curve. So we are measuring this area under the curve, and as b goes to infinity. So it's the limit. I should say this definition is equal to this if the limit exists. If the limit does not exist, then we say the integral does not exist. And then the second picture, it should be obvious as to what's going on here as well. You might have something like this, and maybe you have, and now you have b over here, and this integral from negative infinity to b, we really mean now, let me make my pen, it's a, and a is the thing that is going off to negative infinity, and we're measuring this area under the curve. Okay, and also as a corollary of this, it's easy to define so from this, and this might be a part 3, we can define this integral from negative infinity to infinity, f of x dx. We just define that as the sum. We take any a in the real numbers and take that sum plus the integral from a to positive infinity of f of x dx. And we do this for any constant a. And well, I've run out of room, but let me draw a picture up here. So we literally just pick any a we want to. So suppose our function looks something like this. We pick any. Let me make that a little nicer. We pick any old a we want to, and we just compute the area. And so now we know how to compute this area under the curve, that is just that. And we know how to compute that area under the curve. That is just that. And this integral over the whole real line is just the sum of those. And you can obviously tell that it does not matter what our choice for a is. Okay, so let's do 3 examples. First one, well, the first 2 are, actually, no, the first one we saw in the first slide, the second one was a little bit different. So this first example, by definition, this is equal to the limit as b goes to infinity of the integral from 0 to b of e to the negative x dx. So let's just compute that integral. So the integral is negative e to the negative x from b equals, from 0 equal, or 0 up to b. So this becomes the limit as b goes to infinity of negative e to the negative b minus e to the 0, sorry, minus negative e to the 0, which is 1. And so this limit, when you plug in b equals infinity, that term is just going to go to 0. And again, you're technically not plugging in infinity, but you essentially can do that. I've never gotten in trouble doing that. Okay, so that's equal to 1. The next one, let's compute this integral. This is defined as the limit. Now as a goes to negative infinity of the, I always like to write this as e to the negative 2 dx. So this is the limit as a goes to negative infinity of x to the negative 1 divided by negative 1. So that's negative x to the negative 1 from a to negative 1. Oh, I forgot to put my limits over here. So this is from a to negative 1. And so it's funny, I always like to look at this as x to the n in this form over 1 over x squared. But then when I plug in, I like to write it as a fraction. So this is I'll be a little bit pedantic here and I'll write this as the limit as a goes to negative infinity of negative 1 over x from a to negative 1. So that is the limit as a goes to negative infinity of, I'm going to pull out the negative sign here because that always messes me up to have a minus negative, of plugging in negative 1 gets me a negative 1. Plugging in a positive a gets me 1 over a. And again, this negative sign came from that. But now, everything we have here is positive, so I'm just going to make that positive, positive, positive. And plugging in a equals negative infinity, or any sort of infinity into here is going to make that term. That term is going to go to 0. So our answer here is also going to be 1. So this is a picture. This first one is the area under the curve of e to the negative x. It looks like it's like exponential decay function, and this just says that this area is equal to 1. And the second one is, so 1 over x squared looks like this. Is that correct? Yeah, that's correct. So this is 1 over x squared, and this one says that if we take the integral from negative 1 to negative, so this area under the curve is infinite, well, it's infinite space, but it's finite area, infinite length, finite area, that's going to be equal to 1 as well. Okay, so finally we have this last integral. Now we're integrating over the entire real line. So let's write this as the, let's see, what's the best? So let's pick a number in the real line. Let's just pick 0, because that's halfway in the middle in some sense, in some sense not. So this is the integral from negative infinity to 0 of dx over 1 plus x squared plus integral from 0 to infinity of dx over 1 plus x squared. Now both of these we can write as limits. So this first one is the limit as our bottom limit is a, right? Yeah, a goes to negative infinity of a to 0 of 1 over 1 plus x squared. And this, all right, let me put a dx in there. Let's make that a dx. This second one is the limit as b goes to positive infinity of 0 to b dx over 1 plus x squared. Okay, so both of these are inverse tangents. Okay, so the first one, this is the limit as a goes to negative infinity of inverse tangent, right? Is that, yes, inverse tangent. Now that should be a 1. Now let's erase that and make that a little better. Inverse tangent of x, and this is from a to 0. Again, I'm not good with the pen tonight. A to 0. The next one is the limit as b goes to infinity of inverse tangent. Oh gosh, inverse tangent of something, of x from 0 to b. So this is, let's see if I can fit this in here. So this is, plugging in 0, the inverse tangent of 0. Remember what that is? I always need to think about that. Where is the tangent equal to 0? The tangent is equal to 0, right? So that our domain on inverse tangent, or our principal domain, is in this region. So the tangent is 0 right there. So inverse, so when we plug in 0 to inverse tangent, we get 0. So plugging this in, first one, we're going to get 0 minus, ooh, I forgot to put limit there. I hope I have room here, this one. So this is the limit as a goes to infinity of 0 minus inverse tangent of a plus the limit as b goes to infinity. Oh, the first one should have been negative infinity. That's, you see that's a negative sign? Yeah. Of inverse tangent of b minus 0. Now, where in this little red arc is the inverse tangent actually equal to positive infinity? Remember, the tangent is the y value over the x value. So right here, the tangent of pi over 2 radians is going to be equal to infinity. And when I say equal, I really don't mean it's equal to, but I think we're all grown-ups, you know what I mean by this. And the tangent of negative pi over 2. That's what I like about teaching college, is I can say things like this to you, and you know what I mean. Is so that, in quotes, the tangent of negative pi over 2 is negative infinity. It's the y value over the x value. That's negative 1 over 0 here and 1 over 0 here. So let's go back here, and this is negative pi over 2. Yes, negative. Oh, I'm sorry. It's my. Let's write this. Let's write this out. So this is 0 minus negative pi over 2, because that, remember, there really is a negative sign there. I know it's hard to see. And then here, this one is positive pi over 2 minus 0, and together our answer is pi. I'll box that double so we can see all of these. And now this function here, if you plug it into Wolfram Alpha or your calculator, you'll see that it's going to look something like this. The tangent of the inverse tangent of 0 is just, wait, is that right? The inverse tangent of 0 is just 1, and so this just says that the total area under the curve of this function is equal to pi. I should have made my pen thicker to do that. Oh well. Okay, so type 1, as we saw, is when we have a function that goes off to infinity, either on the left or the right, and so we have a horizontal asymptote. When we have a vertical asymptote, that's when we have a discontinuity in the brand. So, and I know this looks like a intimidating slide, but let's go through it step by step. It's not that bad. So this is saying if f is continuous on AB and discontinuous on B. So let me draw a picture of what that might look like. That might look like if we have something like this. This function is continuous on this half interval, but it is discontinuous at that point. In that case, in that case we define the area under the curve. So the area under the curve from A to B is just the limit. So over here, this is A equals, and this is B equals 0. So we just take this. We take this integral where the thing is continuous, and we just take the limit as the right endpoint goes to B. And if this limit exists, we say that the interval exists. Now, part 2 is just a mirror image of that. So I'll draw it quickly. I won't say much about it, but again, if maybe we have B is here, and maybe we have something like A is there, and if our function is discontinuous there, then the area under the curve from A to B is just the limit of the integral on a finite little piece as the left endpoint now goes to A. And let me actually give you one more case where something like this could happen. It doesn't actually have to be a vertical asymptote. We could have a function, like we could have a nice function like this, and there just happens to be a discontinuity here. So maybe it's defined at this point, and it is not defined at that point. And we want to integrate. We want to say, what is the area under the curve between A and B? And obviously, we know what this should be, right? It's just this little piece of area, but it is discontinuous at B. Actually, this little picture here should be up there, because this is where the right endpoint B is where the discontinuity is. So here we just take the integral from A to T on this, and then we move T and take the limit as T goes to B. And finally, if f has a discontinuity at C, which is between, so this is like before, this is putting these two things together. Suppose we want to integrate over a discontinuity. So maybe one case of that is maybe we actually have a function like That is, so it's possible that's supposed to be a hole up there. Let's try that again. So suppose we have a function that has a true discontinuity at C, and we want to integrate, find the area in the curve from A to B. Well, that's just this area right here. So we do the two sides separately. We do part 1 and part 2. So we do the part 1 on this side and part 2 on that side, and if that exists, then we say that's the integral across a discontinuity. Of course, another way this could look is our discontinuity might actually, it might be more than a discontinuity, it might not even be defined. So something like 1 over x squared like we saw before, we could integrate this from A to B, and C of course is where the function isn't even defined. So we could handle a case like that. And in the third case, we could actually, this is almost trivial, but let's suppose we have a function that has a hole in it. You saw these in high school algebra. And just to be cute, we define the function at C. So that's supposed to be C. So let's suppose that at C, the function, just for fun, is defined to be up here. So that this is like f of x, and there's a hole. So again, we can still integrate across this discontinuity if our limits exist on the left-hand side and the right-hand side. So let's finish with two examples. The first one, the integral of 1 over square root of x from 0 to 1. So this guy here looks like, it's going to look something like this, I think, because it's going to go to 0. So this is one of the cases where there's a vertical asymptote. So to do this, we just use the definition. It's the limit as t goes to 0 from the right of the integral of t to 1 of 1 over root x. So I like writing that as x to the minus 1/2 dx. So again, we are integrating from t to 1. So we're finding this area in the curve, and then we're just letting we're letting this go to 0 and seeing if that limit exists. So this is the limit as t goes to 0 from the right. Again, notice it's from the right because this function does not even exist to the left of 0. Oh, let's see, I don't need the integral anymore. I know how to do this. So this is x to the positive 1/2, positive 1/2 over 1/2. And now I like to go back into square root form. So the limit of 2 square root of x from t to 1, which is the limit as t goes to 0 from the right of 2 1 minus root t. Is that, yeah, so we have this, and as t goes to 0 from the right, root t is going to go to 0 as well. So this is just equal to 2. And there is our answer. Okay, so the next one is the integral of 1 over x minus 1. So okay, what does this look like? So let's see if we can sketch this. 1 over x, we know, looks like that. This is 1 over x. And 1 over x minus 1 is this thing shifted 1 unit to the left because of this x minus 1. So this guy is going to look like, I'm sorry, shifted to the right because it's x minus 1. So it looks like that and that. And we have this horizontal asymptote here. And we want to integrate this. So this asymptote is at 1. And we want to integrate this from 0. Let's see. From, I'm going to change this problem just for fun. It would be more interesting to see what happens if we integrate this from 0 to 2. Why do I say that's more interesting? Because if we do that, we get a nice symmetric area So, you may wonder, even if this area is infinite, is this integral, why can't we just say that's 0? Every little piece of area here cancels out with every little piece of area here. Is that going to work? So I'm gonna change that. I'm gonna change that to 2. So let's see. Let's use our definition. So this is equal to the integral from 0 to 1 of dx. So we take our problem point, not dx, df. Sorry. X minus 1. I just copied that down wrong. Plus the integral from 1 to 2 of dx over x minus 1. So we know how to do each of these. We've seen it before. The first one is the limit as t goes to 1 from the left of, so our endpoint that is moving now is that one, and our other one is moving that. So this is our problem endpoint. So now in this one we're approaching 1 from the left-hand side, so over here, of the natural, let's see, that's the, I'm going to write the integral first. So this is 0 to t dx over t minus 1, x minus 1. Sorry about this today. I don't know why I keep saying the wrong things. X minus 1 plus the limit. Now we want to approach t from the right, so t goes to 1 from the right hand side of dx over x minus 1. Now the integral of both of these is just the natural log of x minus 1. So this here is the limit as t goes to 1 from the left of the natural log of x minus 1 evaluated from 0 to t, plus the limit as t goes to 1 from the right of the natural log of absolute value x minus 1. Now we're going from t to 2. So what is this? So for this first one, I should write this as the limit as t goes to 1 from the left of the natural log of t minus 1 minus, if I plug in 0, I get the natural log of, I'm going to get the natural log of 0, or sorry, the natural log of 1, which is 0. So I'm going to write that as 0, plus the limit as t goes to 1 from the right of, let's see, so we have, if I plug in 2 into here, I get the natural log of 2 minus 1, natural log of 1, which is 0. So I get 0. Didn't matter if I had put 3, I would just get a number. So I get 0 minus the natural log of t minus 1. Okay, right? Is that? Yes. So in this case, both, let's see. So this, it doesn't matter if we're approaching from the left or the right. Both of these cases, we're getting the natural log of 0. That's the limit. So this and this, both of these things are going to go to, I'm going to write it like this, going to go to negative infinity. So this thing is negative infinity plus negative infinity, which is not defined. Actually, plus positive infinity technically. So it's technically it's tempting to want to cancel that and say, oh, that's equal to 0, but you can't do that. And the picture of why these things are negative infinity and positive infinity is because, hey, look, you have this, the area here is negative infinity, the area here is positive infinity. So here we say that the integral is, we're going to say it's divergent. And in the next chapter, we're going to see more reasons why things go wrong when we try to add negative infinity to infinity. It's tempting to say it should work here, but we'll soon see when we study infinite series that we get into a lot of trouble if we try to cancel out these two things and make them zero.